Section 6.3 is called Factoring Trinomials of the form ax squared plus bx plus c. I'm actually skipping section 6.2, although I'll go back and address it after I've shown you how to do 6.3. The reason for that is that once I've shown you how to do these, you simply apply them to the trinomials in 6.2. The only difference is that in this section, a, the number in front of your x squared term, can be anything. It might be a 3 or a 17 for that matter. In 6.2, a is always 1. And that, if I teach that section first, it can lead to errors in this section. But if I teach this section first, you'll find the next section really just falls from this one. So we're going to do 6.3 first, and then go back and briefly address 6.2. Your textbook uses trial and error as a technique. I really don't like that. If you've seen factoring before, you may have a kind of trial and error technique that works for you. And that's fine if you like it, and more importantly, you always get the right answer. But if a trinomial can be factored, then you can put it into a form so that you can factor it by grouping. I'll do the examples in your textbook, but I'll use the factoring by grouping method, not the trial and error method. That way you can read the book and watch the videos and decide which technique is better for you. Here's the thing. 6a squared plus 7a plus 2 can't be factored by grouping in the form that it's in now. We need it written like this. 6a squared, and instead of one term in the middle, we actually need two. Let's see, let's try 6a plus 1a. Now, this is a legal move because 6a plus 1a, if I were to combine like terms, would give me 7a. So I'm allowed to write this way. That's no problem at all. But what happens when I try to do my factoring by grouping? Looking at the first two terms, I get that what's common to both of them is a 6 and one copy of a. What's left over is this other copy of a, 6a times a is 6a squared, and 1, because 6a times 1 is 6a. So far it looks okay. What's common to 1a and 2? Well, nothing. But actually, 1 is common to anything, so you can always put a 1 down as your common factor. What's left over? Well, everything that was there, right? 1 times what is 1a? 1 times what is 2? So I've grouped it and I've factored the groups, but the binomial factors are not common, they're not the same. So I need to find a different way to rewrite these middle two terms. Let's make another copy of this problem and start over. I'll rewrite the middle term, 7a, as 3a plus 4a. That's a legal move. 3a's plus 4a's is 7a's. I've just broken it up. Then I can look at what's common to these two terms and these two terms. What's common to these two terms is 3 and one copy of a. What's left over is 2a plus 1, because 3a times 2a is 6a squared, and 3a times 1 is 3a. The back two terms just have 2 in common. 2 times 2a gives me 4a, and 2 times 1 gives me 2. This time my binomial factors are the same, so I can proceed. My common factor is 2a plus 1, and what's left over is 3a plus 2. When I did it this way, splitting 7 up as 6 plus 1, my binomial factors weren't the same, so I had to find a different way to split up 7a so that my binomial factors would end up the same. This looks a lot like trial and error as well, and the way I've done it here, it is. But there's a way to tell what's the best way to split up your middle term. Let's take a look at that now. I'll redo this problem one more time over here, but this time I'll show you how I decided that 3 and 4 were the best way to split up 7a. Let me start by making an observation. Did you notice that 6 times 2 was 12, and that actually 3 times 4 was also 12? Over here I have 6 times 2 is 12, but 6 times 1 is only 6. So I need a way to split up my middle term so that this product, 6 times 2, is the same as this product. But the other thing that needs to be true about these two numbers is that they have to add up to 7, right? If I were doing this problem in this direction, the next step, the last step, would be to combine like terms. I'm undoing that process, so I still need this middle term to be made up of the sum of these two middle terms in this step. So the 3 plus 4 would have worked, and the 6 plus 1 would have worked as a way to write 7a. But the other thing that turns out to be necessary is that this product, 6 times 2, has to match this product. And in this case it did, and in this case it didn't. That's why this one didn't work. So how do you figure out how to get that? The way I do it is to make a list. I start by noticing what my product needs to be. 6 times 2. 6 times 2 is 12. Now, I know that the two numbers that make up 7 also have to be a product of 12. This one's not too hard to find, especially since we've already done it and we know it's 3 and 4. But if we didn't know that, how might we proceed? I've made a note of my product, and I'm going to make a note of my sum as well. And then I'm going to write all the different ways that I can write 12 as a product of two numbers. Once I've done that, I can take the sum of these two numbers and write it in this column. And when I find the one that gives me this number, I know I've found the right two numbers. So now I know how to break up 7a. Now, we've actually done this problem already, so I'm not going to continue here. All I'm doing with this piece is showing you how I found 3a and 4a. It turns out there are only 3 ways to build 12 as a product of two numbers. Once I start my next one, I can see that 4 times 3 is the same as 3 times 4. And the next way, 6 times 2, that's already up here as well. So I'm duplicating myself. These are the only ways to build 12. We found 3 times 4 is the one that works. If I were doing this problem from scratch, I would just jot down the 6a squared in front and the plus 2 at the back, and then continue factoring by grouping. If either of these numbers was much bigger, then this list can get longer. And where, in this example, it was easy to see that 3 times 4 would work, with bigger numbers, it's not as obvious, so making the list is really quite useful. A little vocabulary. Not so much vocabulary as a couple of new symbols. We could write P for product here and S for sum. But just for fun, let's use the Greek letters pi and sigma. Actually, it's more than just for fun. These are actually the symbols that mathematicians to mean product and sum. So there's certainly no harm in showing them to you. And in fact, it'll probably come in handy later on. Not only that, but you can impress your friends that you know some Greek. Okay, let's try another problem, but we'll do it this way. One more observation before I go on. Your textbook gave 3a plus 2 times 2a plus 1 as the answer. And I'm often asked, are these the same? Well, they are, because really all I'm saying is take this thing here, let's call it a, and multiply it by this thing here. We'll call that b. Since all I'm doing is multiplication, I can do it in either order. So these two things really are equivalent. The commutative property of multiplication says this times that is equal to that times this. So as long as what's in each of your factors is correct, it doesn't matter which order your factors appear in. Example 2 in your text asks you to factor 4x squared minus x minus 3. I'll start out by reminding you that there's an invisible 1 in front of the x. So I'm looking for a way to build 1x. In fact, negative 1x. And there are a lot of different ways I could do this. I could say, let's rewrite this as 4x squared plus 99x minus 100x minus 3. Or 4x squared plus 10x minus 11x minus 3. Or 4x squared plus 56x minus 57x minus 3. In fact, there's an infinite ways of doing it. But we have something very specific that we need to accomplish here. We need for the product of these two numbers, 4 and negative 3, to be equal to the product of these two numbers. 99 times negative 100 is not negative 12. Neither is 10 times negative 11. So we need to find a way to get negative 12 as a product of these two numbers as well. I do need to split up this middle term, and I will write it in between the first term and the last term. The question is, how do we do it? Well, we're going to make a list of our products and a list of our sums. 4 times negative 3 is negative 12. The sum that we want is negative 1. Now that I've noted those, let's see how we can go about building negative 12. The options are positive 1 times negative 12, negative 1 times positive 12, positive 2 times negative 6, or negative 2 times positive 6, positive 3 times negative 4, or negative 3 times positive 4, positive 4 times negative 3, or negative 4 times positive 3. I've run out of room, but actually that's okay because positive 4 times negative 3 is the same as negative 3 times positive 4. Negative 4 times positive 3 is the same as I have here. So at this point, and in fact from there down, I'm just repeating myself. I don't need anything beyond this line here. These are all the different ways that you can build negative 12 as the product of two numbers. Now, take each entry in this column and add these two numbers together. These are all products because I was looking for how to get a product of negative 12. But now I need the sum of these. Positive 1 plus negative 12 is negative 11. Negative 1 plus positive 12 is positive 11. 2 plus negative 6 is negative 4. Negative 2 plus 6 is positive 4. 3 plus negative 4 is negative 1. And negative 3 plus positive 4 is positive 1. Which one of these matches this? Where is negative 1 in this list of numbers? It's here. So since negative 1 was the sum of 3 and negative 4, 3 and negative 4 are the numbers that I need to use as my middle two terms. But I'm rewriting negative 1x. So plus 3x minus 4x is my middle two terms. Just to reiterate, 4 times negative 3 is negative 12, and 3 times negative 4 is negative 12. But in addition to that, 3 plus negative 4 is negative 1. All right, now that we've done that, let's finish the problem by factoring by grouping. What's common to these two terms here? No numbers, or 1. But there's at least one copy of x. What's left over? What do I have to multiply x by to get 4x squared? 4x. And what do I have to multiply x by to get 3x? 3. Now the back two terms. What's common to both negative 4x and negative 3? At first glance, it looks like nothing, but they're both negative. And in fact, if this sign here is negative, remember from a previous example, we're automatically going to make the next thing we write negative and assume that what we're factoring out is negative. There's nothing else that's obviously common to both of these. But remember, 1 is a common factor of everything. So I'm going to write 1 as my common factor, remembering that it's actually negative 1. What do I need to multiply negative 1 by to get negative 4x? Positive 4x. And what do I need to multiply negative 1 by to get negative 3? Positive 3. My binomial factors are in fact the same, so they are common to this term and this term. Therefore, 4x plus 3, the common factor, is brought out, and what I have to multiply by 4x plus 3 to get these two terms is x and negative 1. Shall we check this and make sure that in fact this really does factor as this? This is my answer. I was asked to factor. But if I want to check that my answer is correct, I just need to unfactor. I just need to do distribution. 4x times x is 4x squared. 4x times negative 1 is negative 4x. 3 times x is 3x. And 3 times negative 1 is negative 3. By combining these like terms, I get 4x squared minus 1x, or just minus x, minus 3. That's what I started with. That's how I know that this is the correct factorization of this polynomial. This looks like a really tedious process, but once you've done it a few times, you'll find it's fairly mechanical. It's important to understand that what you're looking for when you try to find the product and the sum are numbers that multiply out to 12 and have the added feature of adding up to this number here, negative 1 in this case. Those are the only two examples in your textbook before it goes on to talk about factoring trinomials using the greatest common factor. That is something else we have to take into consideration, but I think I'd like to do a couple more examples just like this first. So I'm going to resort to the exercises again. Let's do question number 2. Factor 2x squared plus 5x plus 3. Now, if you can see it, that's great. But if you can't, and frankly, even if you can, note that there's a foolproof method for factoring trinomials. It may take writing down a few steps, but it'll mean that you can even do the harder ones. Let's get started. Notice that the product of the first and last terms is 6. My product is 6. My sum, the things I want my middle two terms to add up to, is 5. What are all the different ways that I could write 5x? I could write 4x plus 1x. I could write 3x plus 2x. I could write 2x plus 3x. But now I'm repeating myself. 2 plus 3 is the same as 3 plus 2. So I don't really need this version. So it turns out in this case there are only two ways to write 5x as the sum of two terms. But we need, for the middle two terms, not just to add up to 5, but the numbers in front of the x's to multiply out to whatever we get when we multiply these two. So over here I've made a note that 2 times 3 is 6. And now I'm going to look at all the possible ways to build 6 as a product of two numbers. 1 times 6, 2 times 3. If I keep going, I just start repeating myself. I don't need these last two. 3 times 2 is the same as 2 times 3. Now I'm going to take these numbers and add them. 1 plus 6 is 7. 2 plus 3 is 5. This number matches this number. So these are the two numbers that I need to use for my middle two terms. Not these ones. There isn't even a 1 and a 4 over here. That just won't work. Not for factoring. So this is the version of this problem I need to continue with. What's common to the first two terms and what's common to the last two terms? What's common to the first two terms is x. X times 2x will give me 2x squared, and x times 3 will give me 3x. That's the first group. The second group is what's common to 2x and 3? Well, nothing. Except 1. Remember, 1 is a factor of everything. What's left over? Well, everything. 1 times 2x is 2x, and 1 times 3 is 3. But my binomial factors are the same. They're common, so they're my greatest common factor. What's left over? X plus 1. Let's check our answer. 2x times x is 2x squared. 2x times 1 is 2x. 3 times x is 3x, and 3 times 1 is 3. Combining like terms, I get 2x squared plus 5x plus 3, which is what I started with. Since that means that this is equivalent to this, it means that this is the correct factorization of this expression. This is correctly factored. Question number 34 looks like this. 15t squared minus 79t minus 34. Now that I've been doing this for years, factoring a trinomial automatically now makes me want to do this. Look for my product and look for my sum. My product is 15 times negative 34. That's a huge number. I'm going to have to use my calculator. 15 times negative 34 is negative 510. There are so many different ways to write 510. Negative 1 times positive 510 is only one of them. And then, of course, positive 1 times negative 510 is another. The list is going to be long enough without having to make two entries for each pair of numbers. So there is a shortcut here. I can observe that the sum that I want is going to be a negative number. And then instead of adding, subtract these two numbers. That way, all I have to think about is the 510. I don't have to worry about the negative. So how else can I write 510? I can write it as 2 times 255. I can write it as 3 times 170. 4 doesn't go into 510 evenly. In other words, if I divide 510 by 4, I don't get a whole number here, I get a decimal. So that's not going to help me. 510 divided by 5 is 102. Divided by 6 is 85. 7, 8, and 9 don't help me. But 510 divided by 10 is 51. The next whole numbers I get are 15 times 34. Then 17 times 30. I'm going to need more room for this list. Actually, it turns out that I don't need any more room. The next entry would be 30 times 17. There's nothing between 17 and 30 that goes evenly into 510. And since I've already got 30 times 17 here, just written in the other order, I don't need to continue, because if there's nothing between 15 and 17, then there's nothing between 30 and 34 either. So actually, this is my complete list. This is all the different ways that I can get 510 by multiplying two numbers together. Now, remember that I said instead of adding, let's subtract. When I add these two numbers together, I need to end up with a negative answer. The only way you can get a negative answer as a sum is if one or both of your numbers is negative. Because I was trying to build negative 510, I had either positive 1 and negative 510, or positive 6 and negative 85, or negative 1 and positive 510, negative 6 and positive 85, and the same for all the other entries in my list. Can you see that if I add these two numbers together, I'm going to get a positive number, because this number is so much bigger than this one. Whereas what I had before, positive 6 and negative 85, when I add those two together, I'm going to get a negative number, because this number is bigger, but it's negative. So effectively what I'm doing is subtracting these two numbers. And I need to make a note, at least mentally, of which one's bigger. So when I subtract 1 from 510, I get 509. When I subtract these two numbers, I get 253. 170 minus 3 is 167, and so on. The numbers in this column are the result of adding together the entries in each row of this column. Remember, though, that my middle term is negative, so it was the positive small number and the negative large number that I added together. So these are really all negative. Now, can you see your middle term in this list here? There it is. So that tells me that 6 and negative 85 are the two numbers that I need to use to break up negative 79. That means I can rewrite my problem with, instead of 79t in the middle, negative 85t plus 6t, or plus 6t minus 85t. It doesn't matter. The commutative property of addition tells me that I can put these in either order. And it turns out that your answer will be the same as well, although the factors will be reversed. All right, let's continue. What do 15t squared and 6t have in common? Well, 15 and 6 each have 3 in them, and t squared and t each have t in them. What's left over when I pull out that 3t? 15 divided by 3 is 5, and t squared divided by t is t. In other words, 3t times 5t is what gives me 15t squared. 3t times 2 is what gives me 6t. Here's another minus in this position here. So as I get ready to factor the greatest common factor from these back two terms, because of this minus here, I'm going to be factoring out a negative. What's common to both 85 and 34? Well, 85 can be written as 5 times 17. And 34 can be written as 2 times 17. So 17 is what's common to both 85 and 34. Now that I know that, what would I have to multiply 17 by to get 85t? Well, here's my 85, written as 17 times 5, so it's 5t. 17 times 5 times t is 85t. Now, how can I write 34 as 17 times something? 17 times 2. And here's that minus thing again. I have to be careful here. What I'm really doing is saying, what do I have to multiply negative 17 by to get negative 34? A negative times a positive gives me a negative. Now I can see what's common to both of these big terms here. It's 5t plus 2. 5t plus 2 can be multiplied by 3t to give me this term, and by negative 17 to give me this term. And that's it. It's factored. 5t times 3t is 15t squared. 5t times negative 17 is negative 85t. 2 times 3t is 6t, and 2 times negative 17 is negative 34. Combining these like terms, I get this. Negative 85 plus 6 is negative 79. So this is the correct factorization for this expression. Okay, that one was pretty ugly. Those were some pretty big numbers. The list of products I had to make was pretty big too. And you might have been asking yourself, how on earth did I know this? How did I figure this list out so quickly? Your calculator can help with this. If you hit the y equals button and then type 510, the divided by button, and then the xt theta n button, you'll find that right next to the green alpha button. So y equals, that's a button, y equals, the number is 510, the divided by button, and then the xt theta n button. Once you've done that, hit the second button and then the graph button. Notice that over the word graph on this button, it says table. What we're asking the calculator to do is to give me a table of 510 divided by x, where x keeps changing. So it's going to give me a table of 510 divided by 1, 510 divided by 2, 510 divided by 3, divided by 4, divided by 5, and so on. Once you get into the table, it looks something like this. The x value that your calculator is dividing 510 by is 1, and the result of that division is 510. 510 divided by 1 is 510. 510 divided by 2 is 255. 510 divided by 3 is 170. That's how I managed to make this list. It's also how I knew when to leave something out. 510 divided by 4 is a decimal. I'm looking for whole numbers, so I just left the entry for 4 out. 510 divided by 5, divided by 6, 7, 8, and 9 didn't help. Do you remember my just saying 7, 8, and 9 don't work? This is how I knew. 710 divided by 10, 11 and 12 don't work. And at this point, I ran out of room on my screen, but you can scroll down using the down arrow, and you'll get more entries. Just keep scrolling and writing these numbers down until you find a number that's already on this list. The next entry after this one was 30 times 17, and I already had the 30. 17 times 30 is the same as 30 times 17. So I knew at that point I was just duplicating my entries, and I could stop. This is a complete list of all the ways to write 510 as a product of two numbers. I just did it on the calculator, and you can too. I know these are big numbers, but this is kind of a worst case scenario for you for this class. If your calculator can help you make this list, then it's not really all that hard.